by the time I finish it, will be longer than the actual test is. Remember that the test that you're going to take in class is going to be somewhere around 20 questions. Okay? Maybe 17 questions, maybe 19 questions, somewhere around 20. Okay, so if you guys download the final version of the practice test and it's like 25 or 28 questions long, don't freak out and expect that to be what you take in class. Okay? These are just questions that I think that you guys should do as practice in preparation for the exam. Okay? But it's going to be slightly longer than the actual exam is going to be. All right. So what we're finishing up today is two-dimensional motion. We're finishing up projectile motion. And remember, it's really important that any two-dimensional problem, you approach it by breaking it up into two one-dimensional problems. And you solve each one-dimensional problem separately. Each one-dimensional problem has its variables. So the x problem has the x components of the vectors. The y problem has the y components of the vectors. And the only thing that they share is what? What's the only thing that's shared between the two dimensions? Time. Okay? So you can solve one dimension for time and carry it over into the other dimension. Last class, we did a problem of a projectile on the ground being fired just on a flat plane. Now let's imagine that we were firing something off of a building. And I want to ask the same questions. Okay? So if you were to launch a projectile with an initial speed of, let's say, 35 meters per second at a launch angle of 30 degrees, if you were to launch that off of a building which was 5 meters tall, okay, what would be the maximum height of the trajectory as measured from the ground? So what would be the maximum height as measured from the ground? We call that question A. And then question B, how far horizontally does the projectile land from the building? Okay? This projectile is going to produce a trajectory that looks like this. And the two questions are going to be, what is the maximum height as measured from the ground? And then what is the range, or that horizontal distance away from the launching point that the projectile lands? Okay, but this time we cannot use the fact that the trajectory is symmetric. We talked about that last time, that the trajectory will be symmetric only when what?
Both sides are the same height.
Exactly. When displacement's what? Zero. Okay, when the vertical displacement's zero, or when you start and end at the same height. Okay, both of those mean the same thing. That's the condition for the trajectory to be symmetric. But since the initial height and the final height are not the same, we cannot say that this trajectory is symmetric. That means that the amount of time it takes to reach the peak is not the same as the amount of time it takes to fall down. The distance horizontally it travels going up is not the same as the horizontal distance it travels while it falls down, okay? Those numbers are gonna be different because this trajectory is not symmetric, okay? So let's start by looking at part A. If we want to find the maximum height, what axis do we have to look at? The x-axis or the y-axis?
The Y.
The y, right? Talking about the height, maximum height is going to be in the vertical axis. Because remember, we are treating this like two separate problems. So in the y-axis, we're going to have delta y as a variable, v naught y as a variable, vy is a variable, ay is a variable, and t. The question is, where are we going to put our initial position and where are we going to put our final position? The initial position, this is a good place because we know that initial state, but where should we put the final?
The peak.
At the peak, right? Why should we not put the final on the ground where the motion ends?
Because displacement would be 0 for Y.
No,
Oh,
displacement
not 0.
wouldn't be 0.
Yeah.
Say that again? You wouldn't be able to find the height at all. If you put the final point here,
there,
you
yeah.
wouldn't be able to find the height
Yeah,
because the
okay.
maximum height is going to have to be solved by solving for some sort of displacement, okay? However, if you put the final position here, the displacement is -5 meters. That's fixed. You lose all information about the height of the trajectory if you put the final point here. If you want to learn about that peak, if you want to learn how tall that peak is, you need to investigate the peak. And so we'll put our final point here at the peak. Okay? Now the question becomes, what three variables do we know about the y direction? Initial what? Initial velocity. There's only one initial. Okay, initial velocity. We need to break this vector here up into its y component and its x component. Which one's going to be cosine, the x or the y component?
The X.
The x, right? So the 30 degrees touches the x-axis, assuming we use y as being up and x as being to the right, which is the standard coordinate system that we'll use for projectile motion. So v naught x is the initial speed, the magnitude, 35, times cosine of the angle, which is 30, and v naught y is 35, sine of 30. It's like 17 and a half, I think. Sine of 30 is 1/2. So half of 35, I think it's 17 and a half. Yeah. And that's 30.3. Okay, so we know V naught y is 17.5 meters per second. What else do we know about the y-axis?
The peak. The final Y is 0.
The final y velocity is going to be 0 because the final point is at a peak, and the y velocity at any peak is always going to be 0. Since our final position is the peak, we can say our final velocity is 0. Okay? And what else do we know about the y direction?
The acceleration is 10, negative 10.
Acceleration is gravity, which in this case is -10. Okay? In the y direction, for projectile motion, the acceleration will always be gravity. Since we're calling up the positive y and gravity is down, we'll say that acceleration is -10 meters per second squared. Remember that in projectile motion, the only acceleration is gravity, pointing straight down, okay? There is no x acceleration, that ax is 0. This vector for acceleration points straight down. It doesn't point at all to the sides. There is no x component of the acceleration. So we know enough right now to
Right.
solve for either time or displacement. What are we trying to find here? Displacement, because we're looking for the maximum height. Okay, so let's use the equation vy squared equals v naught y squared plus 2ay delta y. The final velocity is going to be 0. So I can subtract v naught y to the left-hand side and divide by 2ay. So delta y is negative v naught y squared divided by 2ay. Negative v naught y, I said was 17.5. Divided by 2, and ay is negative 10. So once again, you see that the negative signs cancel, leaving delta y being positive, which makes sense because the object goes upwards. .3 meters. So, what is the maximum height of the projectile?
15.
It's not 15.3,
20
right?
point-
It's
20.3.
20.3. Why is it
Because
20.3?
you gotta add the bottom, the 5 the 5
Exactly. That 15.3 meters represents simply your displacement above your starting height. You started here. This is where the projectile started. The projectile ended here. So this is what delta y represents. So that height is 15.3 meters, and this height of the building is 5 meters, then the total height above the ground is going to be the sum of the two. Okay? So taking this information, we can then say that the maximum height is 15.3 meters plus 5 meters, which is 20.3 meters. Yeah. Why is the final velocity 0? The y velocity at any peak is always going to be 0, because at a peak, an object is not rising nor dropping. We put our final position at a peak here, so the final velocity is 0. If we had put our initial position at the peak, the initial velocity would have been 0, but only in the y direction. Okay, the x velocity is not 0. The x velocity continues at whatever it was initially, because there is no x acceleration to change it. Okay? Any questions? All right. Now, let's talk about how to figure out the answer to part B, the range. Something to remember about the x direction is that there is no acceleration in the x direction. That simplifies the 3 kinematics formulas that you guys have, okay? For projectile motion, ax is always going to be 0. That's always going to be true. So, our equations, delta x is v naught t plus delta x is v naught xt plus 1/2 axt squared. Vx is v naught x plus axt, and vx squared equals v naught x squared plus 2ax delta x. These formulas simplify, okay? You lose the second term in each of them, and the second and the third equations say the same thing, that the horizontal velocity is not changing. Yeah.
Professor, but isn't that not always true? Because what if x has an artificial barrier, then that wouldn't.
No, the x acceleration would still be 0. Okay? if for some reason there was an artificial
Oh, that's-
barrier, all of
that's-
that would mean is that
that's
the
the
motion
time.
would
Okay,
end
okay.
at the artificial barrier.
Oh.
Just like the ground. We don't say that the ground changes the vertical acceleration, we just say that the motion ends at the ground. Okay? Any other questions?
So basically, you're just saying for ax equals 0, just cancel out the rest, like the back
Well,
end.
the
Like,
three
it'll
terms,
be equal.
they all have an acceleration and that term is 0.
And then it automatically cancels everything, that's what you're saying.
I'm saying that, yeah, this is always true.
Okay.
And the second and the third equation tell you the same thing, which is that the x component of the velocity is not changing.
Right.
But that's what it means for the x acceleration to be 0. Remember, what does an acceleration represent?
Velocity.
Not a velocity.
But
Acceleration and
Gra-
velocity are the
gravity.
Speed
same.
and direction, right?
Gravity.
Speed and direction.
No, that's velocity.
Oh, yeah,
Gravity.
yeah. Acceleration.
Gravity is a type of acceleration.
Acceleration is
Oh.
speed.
It's what? A change in velocity.
Oh.
Okay?
Per unit
Acceleration is a change in velocity.
Per unit.
Alright, these definitions are important to know. An acceleration is a change in velocity. So if you have no acceleration, you have no change in the velocity. And that's why both of these equations tell you that the final velocity in the x direction equals the initial velocity in the x direction, because there's no
Makes
change
sense.
in the velocity in the x direction. So the second and the third equation don't tell you anything you didn't already know. The only equation that's important is this reduced first equation. So if you want to find the range, how far this projectile goes horizontally, you need to know two things. You need to know how fast it's traveling horizontally, that we know, it's 30.3 meters per second, and you need to know how long it takes the projectile to travel from here to here, meaning how long the projectile's in the air for, what we call the time of flight. Okay? Basically, the x-axis is always going to reduce to the equation the range equals the initial velocity in the x direction multiplied by the time of flight. Okay, this is the important equation in the x direction. Okay, that just comes from the equation delta x is v naught x times t.
Oh, so basically you're saying that the x-axis is not going to be a time factor, so we have to go back to the y to find the time and then plug it back into
Exactly.
the x, because it has the artificial barrier for the y is the ground.
Exactly.
So then we have to go, okay.
Exactly.
Right.
So something else I talked about that he just brought up is that the x direction is not going to limit how long the projectile is in the air for. As far as the x-axis is concerned, that projectile would move at 30.3 meters per second forever. There's no reason in the x direction for it to ever stop. The reason that this projectile will stop moving eventually is because the ground prevents its y motion from continuing. The object goes up, it peaks, and then it comes down, and eventually there's a barrier that prevents it from continuing to move in the y direction. So if you want to know how long is the projectile in the air for, if that's what you're looking for, you have to solve that in which axis?
The y.
Y.
The y-axis.
Yeah.
Okay? My recommendation for any of these problems where they're uneven is to solve for the time of flight in 2 steps. Okay? Solve for how long it takes the projectile to go up, and solve for how long it takes the projectile to come back down, and then add those numbers together. Remember, for an uneven trajectory, those two numbers will not be the same. Those two numbers will not be the same. So you cannot simply find how long it takes to rise and then double it. Okay, because it's going to take a different amount of time to drop back down. Okay?
So basically add them together again.
Yeah, figure out how long it takes to go up to reach the peak and how long it takes to come back down from the peak. The problem is already set up perfectly for us to find how long it takes to go up to the peak. Our initial point is here at the building, our final point is at the peak. If we solve for time, that's gonna be exactly how long it takes to go up. Okay, so the problem's already set up to find that time it takes to go up. So let's just solve for time. For time, we can just use this equation, Vy equals V naught y plus AyT. This is going to be to find the time to go up. This is not the total time. At the peak, the final velocity in the y direction is 0. Subtract V naught y over, divide by Ay, and so the time up is negative V naught y over Ay, which is negative, V naught y was 17.5, divided by negative 10. The negative signs cancel, which is good because time should always be positive. So the time to go up is 1.75 seconds. Once again, because the trajectory is not symmetric, we cannot simply say that the total time the projectile's in the air for is just double that. We cannot say that the projectile takes 3.5 seconds to reach the ground because the trajectory is not symmetric. Really quickly, if I redraw this picture, and here's the trajectory, if I draw a horizontal line from the starting point, everything above that horizontal line is symmetric. Okay? So this 1.75 seconds that I found, that's how long it takes to reach the peak. 1.75 seconds. So accordingly, 1.75 seconds is how long it's going to take to drop back down, but only to that point. So you see it still has more to fall. So the amount of time it's going to take to fall is going to be longer than 1.75 seconds because the trajectory is not symmetric. Okay?
So you're saying that we can just do the symmetrical part on that end, but then we have to also add the next part of the.
I wouldn't recommend doing that. You
Okay.
could do it that way. You could say that I know that going from A to B takes 1.75 seconds, going from B to C takes 1.75 seconds, and then I can solve C to D. Okay, but that requires this weird calculation here.
Right.
Okay, what's easier to do is to just,
Erase everything.
no, still drawn in your guys' notebooks. I just have a finite amount of whiteboard space. What's easier to do is just to do this. This is 1.75 seconds, the time it takes to go up from point A to point B.
Right.
Then solve straight for how long it takes to go down, which is to get from point B to this point C. And then add those two numbers together. That's a simpler way to do it. So if we want to solve for this time down, we need to shift our initial point and our final point. Our initial point can no longer be here, and our final point can no longer be here. Where does our initial point have to be now?
The peak.
The B.
At the peak.
And the final is at the
The
end.
final point has to be
At the end.
at the ground.
Right.
Okay? So we will put our initial point here, and we'll put our final point here. Okay? We're still solving a problem in the y direction because we're still trying to solve for time, and time is always solved in the y direction. Okay? But the variables are different in the y direction because we've changed our initial point and our final point. So delta y, v naught y, dy, ay, t. What do we know about this problem going from B to C? The initial velocity is now 0, okay? I'm still using that same general rule that the velocity at the peak is always 0. But now, the peak is not my final point like it was over there. The peak is now my initial point. Okay, so the velocity at the peak is still 0, but now I say that it's the initial velocity that's 0. Acceleration is still negative 10 because it's still falling under the influence of gravity. That hasn't changed. And if you're ever stuck, you can just figure out which one it has to be by eliminating the other two. It can't be time because that's what we're trying to solve for. It's not going to be the final y velocity because we have no idea what speed this projectile hits the ground with. The trajectory is not symmetric. That's really important to remember. So it's not going to hit the ground at the same speed that it was launched at. Okay? So you have no idea what speed it's going to hit the ground at. So what does the third variable have to be? The displacement. Okay? So somehow we have to figure out what this delta y is.
Which would equal the time, right?
No, delta y and time are different, right? Delta y is a displacement, time is a time. Okay, so they have different units or different measurements.
Right.
So somehow, based on everything that we've done, we have to figure out how far this projectile drops from the peak to the ground. We already solved for it, right? It's the 20.3 meters. Okay? Technically negative because it's a vector. But the point is that by solving for the maximum height, we already know how far the object has to drop to go from the peak to the bottom. So that third variable that we were looking for is negative 20.3 meters. And it's negative because delta y is down and we call up positive. Sorry, can you talk a little louder? You would, for this one, you would just get a negative time. That's all you would get for this equation. But it's really important to try not to make a mistake with the signs, because anytime you're adding two things when you should be subtracting them, then the answer is going to be completely different. Okay, but in this problem in particular, you would just get a, you actually get an imaginary time. You would get the square root of a negative number for this problem. Okay, so you could imagine, oh, let me just get rid of that negative sign, it's not supposed to be there, and you will end up getting the right answer. Okay? But in this case, I'm not saying in every case, there are a lot of problems where if you make a mistake with the sign, you will get the wrong answer. Okay? Now that we know the three variables, we can solve for time. We'll use delta y is v naught y t plus 1/2 ay t squared. V naught y is 0. To solve for time, we have to multiply by 2, divide by acceleration, and then take the square root. So t is the square root of 2 times delta y over the acceleration, negative 20.3, negative 10. Oh, it's so close to 4. So the time is going to be just over 2 seconds. .06 square root is 2.01 seconds. And remember, that's the time it takes to go down. So we know the time it takes to go up is 1.75 seconds. We know the time it takes to go down is 2.01 seconds. And so what's the total time it's in the air for? What's the time of flight?
Adam.
Add it. Right? The time of flight is the time up plus the time down. The time up is 1.75 seconds. Time down is 2.01 seconds. What, 3.76 seconds? And now that we know how long the object is in the air for, we can find the range. It's just going to be the initial speed. It's in the x direction because now we're talking about the x direction. Everything that we've done so far has been a quantity solved for in the y direction. But if we want to know the range, that's a quantity in the horizontal direction. Okay? But remember, time is the same for both directions. Okay? If the object has 3.76 seconds to go up and come back down, how much time does it have to move horizontally? Same amount of time. Okay, time is not different in the two axes. Time is the same across both axes. So the range is just going to be v naught x times the time of flight. V naught x we said was 30.3. The time of flight is 3.76. So the range is 113.9 meters. Okay, so we found the maximum height and we found the range. If you can solve this problem, this is the most complicated projectile motion problem that I'm going to expect you guys to solve. I mean, I could change it. I could make them both at different heights. I could launch it from the ground and land it on a building. Like, there could be different variations of it. Okay? But a projectile motion problem within a non-symmetric trajectory, that's the most complicated problem that I'll have you guys solve. That's really the most complicated projectile motion problem you could think of. Okay?
The trajectories are only this type, or they're all over physics?
Trajectory is just a general word for the path an object takes.
Right, so that's all over physics?
Yeah, physics ultimately, all you're going to be doing is describing the motion of objects.
Yeah.
So a lot of what you're going to be doing is figuring out trajectories. Okay? Yeah.
Why is v naught x 30.3? Is that like a
That's the x component of the initial velocity. And remember, it doesn't change no matter where you are in the trajectory because there is no horizontal acceleration. So if you started by traveling horizontally at 30.3, you're always traveling horizontally at 30.3. And you also had a question? I thought it was the same one? Okay. Does anyone else have a question about this problem? All right, let's do one more projectile motion problem, and then we're going to move on to the next chapter. This is going to be one of the few sections that I'm going to skip outright, assuming that I remember your guys' book correctly. There should be a section on circular motion or uniform circular motion or something of that like in chapter 4 in two-dimensional motion. Sorry, just motion in a circle. That we are not going to do now. We are going to do 2 entire chapters later on circular motion, so I'm not going to waste time now discussing something that we're going to spend 2 entire chapters talking about later on. Okay? So that section in your book, that we're not covering right now. We're putting a pin in that, and we're coming back to that later on in chapters 10 and 11, I think, when we talk about rotation. So the only motion that we're going to do in two-dimensional motion is projectile motion. the only two motions that you ever see, the only two-dimensional motions that you ever see in introductory physics are projectile motion and circular motion, okay? And we're gonna come back and focus on circular motion a lot later. All right, let's imagine that we have a stunt driver filming like a James Bond movie or something, and this involves jumping a little river, okay? So we have a car driving horizontally, and it needs to clear a river that is 30 meters wide, okay? It's jumping from an initial height of 5 meters, and it's landing on a platform that's half a meter tall. My question is, what is the minimum safe speed required to clear the gap? What is the minimum speed that the driver needs to be going to clear the gap? 30 meters might be a little bit too fast. Let's make this 15. He might need to be going like 100 meters per second, which is like 230 miles an hour, okay? I'm not claiming that the numbers are realistic, okay? The numbers are irrelevant, okay? The way to solve the problem is the same regardless of what the numbers are. But then this number is really small. Give me 1 second, guys. I need to make a decision. I always complain to my wife that she gets super indecisive about everything. And then in class, I can never quite decide on exactly what numbers I want, okay? But luckily, she doesn't get to see me teach, so she can't make fun of me. All right, this is gonna be the problem, 10-meter gap. It seems more reasonable. 30 feet, starting about 15 feet up, landing on something that's about 1.5 feet tall.
You said 5 meter.
15 meters tall is the platform that they're launching horizontally off of. And it's important to know that their motion is completely horizontal when they leave, okay? And we want to know the minimum safe speed.
You put 5, that's what I'm saying.
Put 5 meters.
Not 15.
I said 15 feet.
Feet, okay.
Yeah, I was just trying to give you guys these numbers in relative terms. 10 meters is about 33 feet.
Oh, gotcha.
5 meters times 32 feet. 5 meters times 3.2 feet per meter is roughly 15 feet. Ignore the feet. I was just trying to tell you guys roughly what these numbers are if you guys aren't familiar with meters. Okay?
So the safest speed, so like what is the car doing? Is it gonna go straight?
The car isn't going to go straight, right? Because gravity's going to pull it down.
Right.
So the car is going to undergo a trajectory like this. Now there's a minimum speed that will get the car to land exactly here by the time it's dropped.
In a
Okay.
safe place where it's not gonna crash.
Yeah. We're going to assume that there's some sort of ramp that can catch the car. Don't worry about how the car lands. Okay, but the point is that the car needs to clear this gap by the time it drops. Okay, this is where it's going to land for the minimum safe speed. Any faster, and the trajectory is going to look like this, and it's going to land well past the edge of the gap, and so it's going to land well safe, right? Well away from the edge where it's dangerous. Okay, we want to know that minimum speed required so that the car just lands at this point. All right, and once again, you're not worrying about the particulars of how the car lands, or how the car is going to, like how the car safely lands, or how the car speeds up, or anything like that. Okay, all you want to do is make sure that the car can travel horizontally 10 meters in the amount of time it takes it to drop. That's what this problem is. Okay? So we split this up into two one-dimensional problems. We have the x direction and we have the y direction. In the x direction, we only care about three things: the displacement, the initial velocity, and time. Because this is the only equation that we have in the x direction. So the x direction, all we care about is delta x, v naught x, and time. In the y direction, we care about the full complement. Delta y, v naught y, vy, ay, t. And let's start plugging in things that we know. Out of these 8 variables, well actually 7 variables because time is twice. Out of these 7 variables, what do we know? Acceleration is what?
-10.
-10. Okay, so let's use the same y is up, positive x is to the right, so acceleration is -10 meters per second squared. What else do we know?
Is finally for y is 0.
Final velocity
For
for
y,
what?
y is 0.
No, it's not
I mean,
going to
the-
hit
the-
the ground with no velocity, right?
Oh,
It's
yeah,
going to be moving down very fast when it hits the ground. So the final y velocity is not going to be 0. You don't know what the final y velocity is going to be,
Yeah.
right? It's moving initially horizontally, and then as it drops, it's going to gain speed down, and it's going to hit the ground with a high velocity in the y direction. So you definitely don't know what that is. And it's definitely not 0.
Can we figure out the change?
No, t is
Displacement is what? It's not 5.
4.5.
It's 4.5. It's technically -4.5, but why 4.5 instead of 5?
Because you subtracted it from 5
Yeah, you
meters.
start at 5 and you end at half, right? So if you start up here at 5 and you end here at 0.5, then your difference is 4.5 meters.
So the arrow goes lower.
The arrow points down.
Yeah, but it's lower. Like according to the drawing,
Yeah,
it looks like if it's the whole thing.
No,
it's not. It's
No.
landing
it's landed right there.
on
Okay.
this platform. If it drops the full 5 meters, it's landing in the river,
Yeah.
right? You want it to land on the platform where it lands safely. Okay, so it has to land on this half-meter tall platform. It can't land in the river. So delta y is the difference between these two heights, and delta y is downward, and we call it a positive, so delta y is negative 4.5 meters. Okay, what else do we know? It's negative because delta y is down. The car's dropping.
And the initial y value would be 0
The initial y velocity is 0. How
Yeah.
do you know the initial y velocity is 0?
because
So you
it's
start
at
at the
rest.
Not quite. You can start at the top like the object did being
Oh, 'cause-
fired off the roof.
Oh, there's no acceleration.
No, it has nothing to do with no acceleration.
Now I know about
I too don't know.
What did you say?
Is it something about height? Or something?
No.
Because it started from the maximum height.
Okay, that's one way of looking at it. It started from the maximum height, the highest possible. Okay, sorry, I thought you meant it started from the top of like a
Yeah.
roof.
Yeah.
Okay, the maximum height of any trajectory is the peak. And at the peak, the y velocity is always 0. So definitely you can think about it that way. Okay, and that's what you meant, I'm sorry, I
So I need to
misunderstood.
learn to explain still.
Alright, it's okay. That's definitely true. Another way that you can understand it is that if it's moving horizontally initially, it's moving completely horizontally, then what's the vertical component of its initial velocity?
The same thing.
0. Right? It only has a horizontal component of its initial velocity. Okay?
Vertical, you expect vertical.
Wait, what?
If the car is moving entirely horizontally to begin with, so this
Oh,
is the
gotcha.
coordinate system.
Yeah, there's no.
This is the y-axis,
Yeah.
and this is the x-axis.
True.
And I'm telling you that the initial velocity
That makes
of the car is entirely horizontal.
Right.
It's never
Then
going
what's
up.
the y component of this vector?
Zero.
Zero.
It's-
Okay.
Okay, that's why it has 0 y velocity
That's
initially.
another way to explain that.
Exactly, that's another way. Both of those ways, perfectly acceptable. You can either imagine that it starts at the peak, in which case the y velocity at the peak is always 0, or since it's moving entirely horizontally to begin with, its initial y component has to be 0. Both of those, perfectly good explanations. Okay? So we know 3 variables in the y direction. What do we know in the x direction?
Displacement of the X.
The displacement in the x direction is what?
10 meters.
Yeah, you want it to be 10 meters, right?
Yeah.
If it's less than 10 meters, you're gonna hit the water. If it's more than 10 meters, then you've traveled farther than the minimum safe distance. So the minimum safe distance is going to be 10 meters. Okay, and what are we trying to solve for?
The
Initial X.
velocity.
The initial velocity, which out of all of these variables is what?
Why is it not 9.5?
VOX.
Sorry,
Why
what?
is it not 9.5 if it was like, it's in the 10, but then it's 1 to 0.5?
No, the 0.5 platform is how tall it is. Yeah. So it has nothing to do with how far horizontally it's traveling.
So to find the initial velocity,
The initial velocity is entirely in the x direction.
right,
So the variable that we would be solving for is v naught x.
right,
V naught x is the initial velocity because v naught y is 0.
right.
Oh,
Okay.
so I see what you're doing.
Do we have enough information here to solve for v naught x?
Nope.
No.
No. What do we need to know first?
Solve time from
Time.
Yeah,
How do we solve for time?
from the y values and then
The
plug
y
it in.
direction. So the first thing we do is we solve the y direction for time, carry time over here, then we can solve for v naught x, and v naught x is the initial speed. And you're done with the question. Do we know enough to solve for time?
Yes.
Yes. So once you've set up the problem, you should be able to see that everything you need to solve the problem is there. Okay? So let's just go through it, and then it'll give me a chance to explain the logic again as I'm going through it. So first we're going to solve for time. We need to use delta y is v naught y t plus 1/2 ay t squared. V naught y is 0. So we have to multiply the 2, divide by acceleration, and take the square root. So t is the square root of 2 times delta y divided by ay. Square root of 2. Delta y is negative 4.5. And the acceleration is negative 10. So you see how the negative signs cancel? So that time is a real number, not an imaginary number. That's good. Time should not be an imaginary number. That's about 1, because it's 9 divided by 10. So 0.9 square rooted is 0.95. So it takes the car 0.95 seconds to fall 4.5 meters. Okay? So the question is, how fast horizontally does it have to be traveling to cross 10 meters in the 0.95 seconds it's in the air for?
So 10 over
10 over 0.95, right? And that's exactly what you get if you just carry the time over. Okay? And then you use the only x equation that we have. The only x equation that we have is delta x is v naught x times t. So the initial velocity, v naught x, is delta x over t. Delta x, how far it has to go, is 10 meters. And the time, how long it's in the air for, is 0.95 seconds. So it's a little bit faster than 10 meters per second. 10.5 meters per second, something like 22 or 23 miles an hour. Okay? What did we actually solve for here? What number did we actually solve for? The initial velocity in the x direction.
Right.
What were we actually looking for? The
Trajectory.
total initial velocity. In no formula do you guys have will you see that total initial velocity. You're going to have a set of formulas where you have the initial velocity in the y direction and a set of formulas where you have the initial velocity in the x direction. This is something that you guys have to do a lot, is that you have to take the information that the formulas give you and you have to transform it somehow into the information that the question is looking for. Initial velocity is a vector just like any other vector. So if you know both of its components, the initial velocity in the x direction and the initial velocity in the y direction, how do you find its magnitude? The Pythagorean theorem, right? Any vector, you can find its magnitude by using the Pythagorean theorem. So the total initial velocity is going to be the square root of the x component squared plus the y component squared. But what's the y component? 0. What's the square root of the x component squared? It's just the x component. So that's the important thing to recognize here. That in this problem, the initial velocity is just the x component of the initial velocity. Because there is no initial y component. So as soon as we've solved for the initial component in the x direction, we've solved for the total initial velocity, which is what the question was asking for. Okay? Any questions?
So you find the total initial velocity with the Pythagorean theorem, which is the magnitude? What do
Yeah.
you say about the magnitude? Is the total initial velocity?
Yeah.
So it's the same thing.
When the problem asks what is the initial velocity, the problem is not specifying either component, so you assume it's the magnitude of the entire vector. So whenever a question asks that, if it asks what is the acceleration, what is the displacement, what is the initial velocity, what is the final velocity, those are all vectors. In none of those questions does it specify a component, so you have to assume it's talking about the entire magnitude. But in this problem, because the y component was 0, the magnitude is just the x component. What was your question? Yeah. Okay, so you have to assume that in the wording of the problem. That if the problem says, what is the initial velocity of the car, you are assuming that this initial velocity right here is v naught. It's the magnitude of the entire initial velocity. It's not going to be v naught x or v naught y. This is not saying what is the initial velocity in the x direction or what's the initial velocity in the y direction. It's not asking for a component, it's asking for the magnitude of the entire vector. Okay? Any questions? All right, so that's it for chapter 4, which is motion in 2 dimensions. If you guys look in your textbook, most of chapter 4 are going to be the definitions of like displacement and velocity and speed and acceleration, and all those definitions, we did that in chapter 2. That's why chapter 4 felt so short, okay? It's because I did the definitions early. All right, and then remember that we're not doing circular motion, so assuming there's a circular motion section in chapter 4, which I'm pretty sure there is, skip it. Okay? All right. Now what we're moving on to is chapter 5, which is Newton's laws of motion.
This was chapter 4, you said.
What we were just doing was 2-dimensional motion, which was chapter 4. Okay? Now we're doing chapter 5, which covers Newton's laws. Okay? The way that you guys should think about kinematics is that kinematics answers the what question of motion. All that kinematics does is it describes the motion of the object. So if I ask you, what is the object doing? That's a question that kinematics can answer. Okay? Kinematics answers the what question of motion. Meaning, what is the object doing? Okay? It simply describes the motion. But a big part of physics is not just the ability to describe what is happening, but to answer why something is happening. Okay, so we need to talk about the why of motion. Okay? Most people use the word mechanics or dynamics as the subject that answers the why question. Okay? Mechanics will tell us why an object does something, not simply what the object does. Okay, kinematics will tell us what the object does. We have these formulas in kinematics that will tell us how far an object will move, or how fast an object will be moving, or how long it will take the object to move that distance, right? Or what an object's acceleration will be. But nowhere in our study of kinematics does it explain why the object moves to begin with. We also assume that acceleration is constant every time we do kinematics, and that's fine. I told you to trust me that most problems we're going to have constant acceleration. I told you that gravity, if I drop an object, produces a constant acceleration, but nowhere did we answer why these objects have constant accelerations. Why is the acceleration of gravity constant? Why, for a lot of problems, can we assume that the acceleration due to the acceleration in general will be constant? Okay? These why questions need to be answered. It's not enough to simply describe the motion that's occurring. We need to also explain why the motion occurs to begin with. Okay? And there are several different ways to answer these why questions. We'll see a few of them, but the one that we're starting with now is known as Newtonian mechanics. Okay? It's because it was developed by Isaac Newton, and it was the first complete mathematical description of physics. Okay? It was everything that we knew at the time, and it was a complete, concise mathematical description of the natural world as we knew it. It was first published in 1687, so this stuff is very, very, very old. And it still works just as well today as it worked back in 1687. Okay, physics hasn't really changed since then. At least not what we're doing. Okay, we've discovered new realms of physics. For instance, Newtonian mechanics doesn't really work for things that are very, 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 very small. Things like an electron. Okay, but in Newton's time, they didn't even know that electrons existed. We didn't discover the electron until like 1891 or something like that. Okay, a couple hundred years later. For really, really, really tiny things, we needed a different version of mechanics called quantum mechanics. That's a study of things that are very, very tiny. Okay? Newtonian mechanics also doesn't work for things that travel very, 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 very fast. And when I say very fast, I mean relative to the speed of light. Okay? Even today, we don't have things that travel anywhere near the speed of light. The fastest object that human beings have ever launched was the satellite that went to Pluto called New Horizons. Do you guys remember seeing the pictures of Pluto?
Yeah.
When those came out, I think in like 2016 or 2017. New Horizons went 16 kilometers per second.
It's not a planet anymore now, right?
No, Pluto is considered a dwarf planet.
Yeah.
Okay? 16 kilometers per second is really, really, really fast. Okay, it's like 11 or 12 miles every second. It's really fast. But the speed of light is 300 100,000 kilometers per second. Okay, which is much, 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 much faster. Okay, 16 divided by 300,000
Damn.
times 100 to convert its percentage. That means that New Horizons, the fastest thing that we have ever built,
187.
traveled at 0.0005% the speed of light. Sorry, it's one extra zero. So even today, we are nowhere near achieving speeds close to the speed of light. But if you were to travel at speeds close to the speed of light, Newtonian mechanics wouldn't work. You would need a new version of mechanics called relativistic mechanics, which was developed by Albert Einstein in the early 1900s. Once again, several hundred years after Newton. And the reason why these new fields were developed hundreds of years later was because they just weren't relevant at the time of Newton. What was relevant at the time of Newton was the motion of objects that we could achieve near the surface of the Earth. So if I throw an object through the air, okay, that motion was relevant to Newton, okay? And then the motion of planets in the sky, okay? That motion was also relevant to Newton. And both of those are described perfectly well by Newtonian mechanics, which is what we're going to talk about now, okay? In Newtonian mechanics, the central thing that is responsible for everything is the force, okay? When we're describing the motion of an object, the shape of the trajectory is determined by the acceleration. I can't explain to you guys why that's true, that involves calculus, okay? But just take my word for it, the shape of the trajectory is determined by the acceleration. And in Newtonian mechanics, the object or the thing that determines the acceleration is the force, okay? So force is responsible for acceleration, and acceleration is responsible for what your motion looks like. So ultimately, if you want to know why does an object undergoing projectile motion, why does it produce a symmetric trajectory? Why does it move in an arc? Or why does a planet travel in nearly a circle around the sun? Or why this or why that? Ultimately, you need to study forces in Newtonian mechanics. Forces provide the why. Okay? So that's where we're going to start. So forces are the central objects in Newtonian mechanics. Newtonian mechanics in theory could solve any problem that you wanted it to within the bounds of where it applies. Like I said, it doesn't apply to things that are very, very small. It doesn't apply to things that are very, very fast. But within the bounds of what it applies to, Newtonian mechanics could answer every single question you could ever possibly want to ask. It turns out, though, that for certain questions, it's very difficult to use Newtonian mechanics to answer them. So people in the centuries after Newton came up with alternative forms of mechanics to basically answer the same questions. But for certain questions, they're going to be easier. Another form of mechanics that we're going to study is basically what we would call Hamiltonian mechanics, named after this other guy, Hamilton, who came in the 1700s after Newton, so roughly 100 years later. And the central object in Hamilton's study was not forces, but it was energy. Okay, so chapter 5 and chapter 6 focuses on Newtonian mechanics, and we're going to talk a lot about forces. Chapter 7 and chapter 8 focuses on energy, which was Hamilton's method of solving mechanics. Okay, so we'll talk a lot about energy in those chapters. But ultimately, there's going to be a central thing that you're going to study, and that central thing is going to describe why motion occurs the way that it occurs. Okay? We're going to run into a problem immediately with force, which is a problem that we've run into repeatedly at this time, up to this point, which is that it's a word that we use every day. But in everyday language, it's a word that we use extremely poorly relative to what it actually means in physics, okay? Your everyday intuitive understanding of a force is probably not what a force is actually defined as in physics.
Star Wars.
Hmm?
Star Wars.
Well, yeah, that's the force, right? I did say the force multiple times. I wasn't referring to like a force field like in Star Wars, okay? But I just meant the concept of a force, okay? But we can start with what we would call a naive definition, just like a guess as to what a force is, and we can develop a better definition of a force as we go along. This is a popular way of defining complex concepts in physics, is you first start with a naive guess. And we'll start with what you think of as an everyday force, and we will better our definition of a force as we go along in our discussion. So first, a naive definition of a force. What do you guys think of when I say the word force?
The energy behind the motion.
No. Force and energy are
Separate.
separate. What were you saying?
And apply
I was just-
pressure on something, with matter.
Pressure is related to force, but it's a different quantity. What do you guys think of when you think of a force?
Something
A
being,
push or
yeah.
Amount
a
of work like exerted.
Work is another quantity that's related to a force but different than a
Ooh,
force.
this is tough. This is
Okay, an attraction, a push, or a pull. Okay? So the most common starting point that you see in most textbooks, most people approach by initially starting with a force as just being a push or a pull. But the problem is that this definition of a force is too narrow. There are other forces that are not pushes or pulls that are not included in that definition. Because as far as that definition is concerned, if it's not a push or it's not a pull, then it's not a force. Okay? But if I hold my marker here and I let it go, why does my marker drop?
Gravity.
There's gravity. And gravity exerts a force on my marker pulling it down, but nothing is physically reaching up and grabbing my marker and pulling it down. So there is no push or pull, and therefore this definition is missing gravity. Okay? If I push my bag, then I exert a force on my bag, but the moment I let my bag go, the bag slows down. Why does the bag slow down? Because of the friction on the tabletop. Friction is another force, but once again, there aren't like little men on the tabletop pushing or pulling the bag to slow it down. So friction would not be classified as a push or a pull, so friction is also missing from this definition. Okay? There are a lot of forces that you can describe as pushes or pulls, but I just gave two that you can't. Okay? Ultimately, what a force is going to be is it's going to be something that satisfies these three rules that we call Newton's laws. So we're going to go through those rules, and as we do, we're going to develop a better and better definition of a force. Okay, so that's where we're going to start next class. Okay? Any questions?
No.